let's analyze a different configuration of their branch cut. So again, here are two branch points. And since the finite segment as a branch cut didn't work, let's switch to the combination of two semi-infinite branch cuts. We know that this branch point is problematic because it gives us the wrong solution which asymptotically large at large values of positive x. However, we can't escape this point at all. So one of the possible contours again is related to this point, and it starts at t equals kappa and again goes to minus infinity. However, due to this configuration of the branch cut, there is additional contour which starts at minus infinity, circles around this minus kappa branch point, and returns to minus infinity. And this is the source of our hope, because again, when we perform the asymptotic estimate for the solution defined by this C2 contour this time, the integral will be defined by the vicinity of this branch point according to Watson's lemma. And hence, it will be dominated by the exponential e to minus x multiplied by t equals minus kappa. So minus x kappa. So that's our hope. And indeed, let's analyze the solution, which is given by this contour. Well, naturally, as we just stated, at large values of x, the solution will be dominated by this exponent. Well, in fact, you can perform this analysis yourself and figure out the value of this prefactor. In fact, there will be some kind of power law function here in the denominator, and it will be your job to estimate the concrete prefactor and this function, power function in the denominator. But I hope right now I'm convincing enough with this leading asymptotic behavior. So let's check out for the second condition, because our wave function should vanish at psi equals 0. So if this contour good enough, can we actually arrive at this condition? Let's see. So psi of 0 is the contour integral from our pre-exponential function, which is t minus kappa to the corresponding power divided by t plus kappa. Well, luckily enough, this integral can be computed exactly. There is actually an antiderivative. Well, to see it, it's better to switch, to change slightly the variables. So let's do this. Let's shift the variable. Let's introduce t plus kappa equals s. Then the structure of the branch cut stays essentially the same. Now we just shift by kappa to the right. And the second branch point is shifted to point 2 kappa. And our contour is a classical Hankel type contour. Right. So after this change, the integrand becomes s minus 2 kappa divided by s. So actually it's right. So s minus 2 kappa divided by s and ds over s squared. And let's rewrite this expression in curly braces as follows. Так, тут пауза, естественно. So it's simply 1 minus 2 kappa over s. And the antiderivative is transparent. it's simply 1 minus 2 kappa over s to the power of kappa over gamma over 2 kappa, divided, I think, by gamma. Is it so? Let's check. Yeah, I think so. I think that's true. Right, and we should take the difference of these two antiderivatives at point minus infinity and minus infinity. So don't get confused, because these are two different minus infinities. The upper one is taking at the upper bank of our branch cut, and the lower at the lower bank. So to figure out the difference between these two values, we should again define the regular branch of our g of t or g of s function. And well, what would be the suitable choice? Actually, it's not that relevant, but let's choose the value of our g function such that when it's positioned slightly above the right branch cut, it's positive. So g of s plus I naught, I0, when s is real and greater than 2 kappa, is positive. That means, for example, that when we go from this infinity to, for example, minus infinity in the upper complex semiplane, then the complex number s rotates by pi, as well as complex number s minus 2 gamma, 2 kappa rotates by pi. And here we have precisely this combination of complex numbers, right? It's s minus 2 kappa divided by s. So when we want to find the value of our multivalued function at minus infinity above the branch cut, we just get 1, because these two pi direction, they cancel each other, since both of the functions, these functions are positioned at numerator and denominator of our fraction. Right, so at minus infinity above, this expression gives us simply 1. At minus infinity below the branch cut, there again the s function makes a clockwise rotation, so that means negative rotation, and the change of the argument of its argument is minus pi this time, while the change of the argument of the s minus 2 kappa function is again pi. So this time the combination of these two changes of the argument won't cancel, they actually add up. So minus pi in the denominator and pi in the denominator. As a result, we get e to 2 pi I multiplied by kappa gamma over 2 kappa. So this is the value of our wave function at the origin, and it should vanish. And indeed, we can achieve this by setting the value of the corresponding exponent of our exponential function, which is gamma pi divided by kappa, to 0, or rather to 2 pi n, where n is arbitrary positive or negative integer. However, since our kappa is positive and gamma is positive as well, then n is assumed to be positive. And as you guess, this gives us the correct quantization of energy levels, because kappa is related to our energy as follows. So now kappa is simply gamma over 2n. Or let's rewrite this expression in the following manner. It's gamma over 2 kappa is equal to n. Here, however, is hidden some subtlety is hidden. Why? Because if gamma over 2 kappa equals some integer, then the whole analytical structure of our solution changes, because all our multivalued function here and here becomes single valued. So, however, this final outcome that kappa should be quantized remains the same. So let's briefly sketch what's going to happen with the whole this analytical structure of our solution, and then write down the final quantization of energy, which is given by this expression.